All right, we're going to look at two different practice problems that are dealing with uniform acceleration. But before we do that, I want to look at our kinematics equations, and I want us to list which variables are in the equation. And the reason why we're going to do this is I want to identify what equations can be used in what scenarios. For example, if we take a look at the top equation here, it has the final velocity, the initial velocity, acceleration, and time in our equation, which means that we cannot look for the displacement. So we cannot use this equation to get displacement, or at least not on its own. If we look at the second equation, we see that it has both initial and final position, initial velocity, acceleration, and time. So this is useless for finding the final velocity. We would need a second equation to get that done. The third equation has both velocities, has acceleration, and distance. So this allows us to solve for variables without needing the time interval. And the fourth equation here uses the displacement, which, if you recall, displacement is just the final minus the initial. So how I've written it on here, although I think I'd rather it be the other way around. So final position, initial. So keep in mind, displacement is just the difference between those two. We see that we have both velocities and we have time. So this equation allows us to solve for variables without needing the acceleration of the object. However, all of these equations assume that the acceleration is uniform. So this means not only is the object constantly accelerating, but the rate of the acceleration is also consistent. So it's always accelerating, and it's accelerating at the same rate. So let's take a look at number one. It says a jet plane lands with a velocity of 100 meters per second in the positive direction and can accelerate uniformly at a maximum rate of -5 meters per second squared as it comes to rest. Can this plane land at an airport where the runway is 0.8 kilometers long? There are two ways we could do this. We could solve for the distance the plane needs to stop and hope that it is less than or equal to the length of the runway. Or we can solve for the final velocity after that 0.8 kilometers and check if it is equal or less than 0. So if it's less than 0, that tells us that the plane would have had enough time to stop, and if it kept accelerating, it would start to move backwards as well. So if we get a positive number, that tells us that the plane would not have stopped. All right, I think it's easier just to see what distance would be required to stop. But first, let's take a look at the information we have. Our 100 meters per second in the positive direction is our initial velocity, because the plane is coming in for a landing, so it's coming in at 100 meters per second. And our goal, hopefully, is for it to stop. If it comes to a stop, that tells us our final velocity is 0 meters per second. We know the acceleration is a -5 meters per second squared. And we're checking to see if the distance is less than 0.8 or equal to. We do not have the time here. So no time, sad face. If we take a look at our equations, we see that the third equation is the one that doesn't need time. final squared equals initial squared plus 2a delta x. And we're checking to see if this is 0, or sorry, if this is 0.8. I would move everything around first, so I would subtract the initial velocity from both sides, and then divide both sides by 2a. So we have our difference of squares up top, and we're going to divide by 2a. 0 squared minus 100 squared over 2 times a negative 5. Let me do some quick math. 100 squared divided by a negative 10 should give us 1,000. So we need a full kilometer. So that's 1 kilometer. That is greater than the 0.8, so the plane won't be able to stop. We could even double check this. If we wanted to know the final velocity after 0.8, we could assume delta x is 0.8, and we want to know, okay, is this equal to 0? So instead we're looking for the final. V squared equals V naught squared plus 2a delta x. So it's starting out at 100 meters per second. Then we're going to add 2 times a negative 5 times 0.8. Uh, 2 times negative 5 is 10. Or negative 10, and then times the 0.8. So that's a negative 8. And from there we see that we're going to end up just shy of 0. All right, let's take a look at this one. It says the police find skid marks 60 meters long on a highway showing where the car made an emergency stop. Assuming that the acceleration was negative 10 meters per second squared, the car was exceeding the 80 kilometers per hour speed limit? Justify your answer. Well, we have here the displacement, the final velocity, and the initial velocity, along with the acceleration. Once again, time isn't mentioned. So we would still use our same equation from earlier, except we're given a speed that's in kilometers per hour. So in order to solve this, we would take the 80 kilometers per hour and we would convert it back to meters per second. So that way it matches the acceleration and the displacement. So 1 kilometer is 1,000 meters, and 1 hour is 3,600 seconds. Let's do some quick math. So it looks like it's about 22 meters per second. Hey. And that's how you'd solve for.
Well,
You're good.
look for